Hi, so welcome to Lesson 2 in Permutations. Today we're going to look at more organized counting, and we talked a little bit at the end of Lesson 1 about restrictions, about saying, well, there needs to be at least one of these, or none of those, or two or three of those. And so we're going to talk a little bit more about restrictions and without restrictions. So when we count the total number of outcomes without any restrictions, we're able to use all of the possible options available, as well as often using them more than once. Okay, so if it's not stated, then usually repetition is allowed. Like if any restrictions are not stated, then you can assume that it's limitless, that you have no restrictions.
Yeah.
Restrictions are placed to limit which options we can choose from and or to limit the number of times we can use them. So maybe we can't use it here, but we can use it here, like the 0. We can't put it in the first digit, but we can put it in subsequent digits. Or we may say, well, we want to use this 2 or 3 times, or we can't use this more than once. So in permutations, we may have restrictions on which items can or cannot be grouped together, how many times we can use them, or where we end up putting them. Okay.
So let's take a look at an example of some restrictions that we might encounter.
Yes.
So here is ice cream cones, and we've got basically a question that's asking us, how many different 3-scoop cones can be made from vanilla, chocolate, and strawberry?
Yeah. And I can distinguish between the scoops. I can tell there's a bottom scoop, a middle scoop, and a top scoop.
Yeah.
Okay.
So what we're going to do is, again, we're going to say, okay, well, repetition is allowed because a chocolate is different than a strawberry.
And they didn't say that repetition wasn't allowed.
Exactly.
So notice that they're not giving any restrictions, so that means we can use things more than once.
Okay. So here's our 3 spots. And we're going to say in the first spot, this is scoop 1. In the second spot, this is scoop 2. And in the third spot, this is scoop 3.
3 stages.
So how many options do I have for scoop 1? How many different flavors can I put in this top scoop?
3.
There are 3 of them. There are also 3 flavors that I can put in the second scoop and 3 flavors that I can put in the third scoop. And this is, of course, again, the fundamental counting principle, because I'm making a choice at each stage. First scoop, second scoop, third scoop. And so I can have 27 different 3-scoop cones with just these 3 flavors.
Yep.
All right, moving on. We also want to include therefore statements, especially when we have a word problem like this, and we're kind of doing our notation here. We'd want to end off with a therefore the number and total number of 3-scoop cones that we can make is 27.
Yeah.
Okay. So moving on, how many different cones can be made if each flavor can be used only once? So each scoop must be unique. Now we have a restriction.
Yeah.
And it basically says, I can't do this. I'm not allowed to have a chocolate.
No.
I have to have all different scoops. However, a strawberry on top is different than a strawberry on the bottom.
Yeah.
Right? Because that would be a different cone. It's a different flavor experience.
Yeah, I mean, it depends which direction you eat the ice cream cone from.
Yes, exactly. So here, no repetition is allowed. What we want to do is very similar. We set up our 3 spots for scoop 1, scoop 2, and scoop 3. And in the top scoop, we have, of course, 3 choices. Because we haven't limited anything. So we've got chocolate, strawberry, or vanilla. But once we've used that scoop,
once we put that chocolate there, say,
now we come to the second scoop. We can't use it again. So now we're limited to, we only have 2 choices.
Yeah.
And once we've hammered that one in place, or I should say scooped that one in place, now for the last scoop, we don't even have a choice anymore, so we just multiply by 1. There's only 1 option left. And so all of a sudden, if we have to make a unique ice cream cone, or each scoop has to be unique, I've only got 6 options.
Yeah.
So from 27 down to 6, and this is quite the restriction, right? And you'll see that restrictions usually cut down the number
from your unrestricted
options, right? So here, the number of cones without any repetition of scoops or flavors is 6. Okay. All right. Now we come to a different type of wording that we're going to see a lot in the next, really for the rest of the year. And it's this concept of at least.
Yeah. At least or at most.
At least or at most.
Yeah.
How many different cones can be made where at least 2 scoops are the same flavor?
Yeah.
So here, again, we're saying, okay, 2 scoops can be the same.
But we can also have more.
But we can also have more. We could have 3 scoops be the same. That still fits our criteria of at least.
Yeah.
So what we don't want here is basically all unique scoops.
Yeah.
Right? So what we say is, okay, how many different cones can we make where at least 2 scoops are the same flavor? Okay, just like in the example that we left you with at the end of last lesson, where we had at least 1 5 must be used. Now we have at least 2 scoops must be the same. You saw in the solution that we took up in class this kind of introduction of cases.
Yeah.
And so you have to kind of divide this into 2 separate parts where we say, okay, 2 scoops can be the same.
Yeah.
3 scoops can be the same, but we have to treat those differently.
Yep. And then because I'd be happy with 2 scoops the same or 3 scoops the same.
Yeah.
And again, I'm rewording it to myself. I know that eventually I'm going to add this together.
Yeah.
Yeah.
Yeah. Yeah. So how do we do this? What's the plan of approach? Well, case 1, we've got 2 ice cream scoops that are the same. Case 2, we've got 3 ice cream scoops that are the same.
Yeah. Now, case 1, you run into a bit of a challenge here because you need a little more space and a little more patience, because when you can have 2 scoops the same in 3 different positions, then you can have like same, different, same, different, same, different, same, you know, and so you need to be able to set up for yourself different groups of 3 lines so that you can create your different scenarios. So in fact, there are even cases within this case.
Yeah.
Like this case has its own cases.
Yeah.
Okay.
So here's the first part of case 1, where I've got the top and the middle are the same, but the bottom is different.
Different, yeah.
Here, I also could have the top and the bottom be the same, but the middle is different.
Yep.
And if you're following along and you're following with our logic, you'll say, okay, yeah, there's one more, and that's where the top is different, but the middle and the bottom are the same.
Yeah.
Okay.
And now you got to populate these with numbers.
Mm-hmm.
Okay, so when you go to place that first scoop, you do have 3 choices.
Mm-hmm.
But then the next one that should be the same as the first one, whatever you chose, it's your only choice.
Yes.
Right?
So here, what we've got is, okay, for this top scoop, we've got 3 choices.
Yeah.
But because the middle scoop has to be the same as the top, I don't have 3 choices anymore. I've got 1 choice. It's got to be exactly the same as this.
Yeah.
Well, how many choices do I have for the one that's different then? Well, I've got 2.
2, because you've used 1 flavor only.
Yeah.
Sure, you've used it on 2 different scoops, but you've only used up 1 flavor.
Yeah.
So you do have 2 flavors left.
Here, the pattern follows exactly the same.
Yeah.
We'd have 3 options up here, but where it has to be the same, we only have 1 option. And so the remaining scoop, the one that's different, we'd have 2 choices.
And I'm just going to add in here that at this point, what you want to do is you want to place your restricted scoops first. So if we were to show you the order we'd write this in the first example, I'd write the 3 and then the 1, because the first scoop, I have 3 choices, and then the next restricted scoop is the one that has to be the same as the first one. And then the last scoop is really sort of unrestricted, except for the fact that it just can't be what the other ones were.
Yeah.
Okay? Yeah. And then for this middle one, well, we've got 3 choices for the first scoop, but then I have to go to the next restricted scoop, which is the last one. So I would place the 3, then the 1, and then once I've placed those 2, I'll say, okay, I've used up a flavor, and now I have 2 flavors left. So you won't logically go 3, 2, 1. You're going to logically go 3, 1, and then 2.
Mm-hmm.
Okay.
So here we'd have the middle scoop. We'd have 3 options for the middle scoop.
Yeah.
We'd have 1 option for the bottom scoop.
Yeah.
And then we'd have 2 options.
And that would be the way you'd logically think about it and write it down. Yeah.
So 3 times 2 times 1 is, of course, 6. The word or implies an addition, because this is okay, or this is okay, or this is okay. Yeah. But they can't occur at the same time. You can't have this arrangement of different scoops and this arrangement of different scoops. It doesn't work. It doesn't happen simultaneously. No. Your ice cream cone is either this or it's this. Yeah. And so we add those together. So we get 6 plus 6 plus 6. which is a total of 18 different ice cream scoops where 2 are the same.
Same.
Now, if we want the ones where 3 are the same, then we look down here at case number 2, where 3 are the same. And of course, how many options do we have? Well, we can have all chocolate,
Yep.
we can have all vanilla, or we can have all strawberry.
Yep.
But that's it. Those are our 3 choices.
Yeah.
So, here we are at the end of this problem, and we say, okay, well, what do we do? I've got an 18 and I've got a 3. These are 2 different cases, and they're 2 different mutually exclusive cases.
Yeah.
The additive counting principle says that we take this and we take this, and because they're mutually exclusive, we add them together.
Because we can't be simultaneously 2 scoops the same and 3 scoops the same at the same time. That's what makes them mutually exclusive.
Yeah.
Yeah.
So we have 21 different options.
It's a lot of different ice cream cones.
Yes. Interestingly enough, this is a lot of work.
Yeah, this is a lot of work. Yeah.
Is there a simpler way to do it?
Oh, there is.
Yeah.
There is a simpler way.
It's a simpler way, but again, it relies heavily on logic.
Yeah.
So in parts A and in parts B, we looked at, okay, the total number of cones, who cares, no restrictions.
Yeah.
Then in part B, we said, okay, here's a restriction. Each cone has to be unique.
Unique. So no repetition.
Then in part C, we said, hey, at least 2 have to be the same. So really, all we were saying, if at least 2 have to be the same, 2 the same, 3 the same, the only thing that we don't want is for them each to be unique.
Yeah.
So we introduce what's called the indirect method.
Yeah.
And sometimes it's easier to count the number of outcomes that we don't want and then subtract it from the whole.
Yeah.
So if you look at the answers to these 3 parts, A, B, and C,
yeah.
the total number of cones possible that we had without
restrictions
was 27.
Yeah.
Okay. And the total number of cones where every single scoop is unique was 6.
Yep.
27 minus 6 is not a coincidence that it's exactly the same
as the 21 that we got.
As the 21 that we answered.
Yeah. Now, our
part
answer was what you would call the direct method.
Yeah.
Which is whatever you want, you set up cases for what you want, and then you add all those cases together.
Yeah.
Whereas an indirect method is where, if the number of cases you want is a greater number of cases, greater number of calculations than what you don't want, it's just easier to take the total without restrictions, subtract out the ones you don't want, and then you'll be left with all the cases that you did want.
Mm-hmm.
So what we were doing previously, you could go back to your note and write, this is called the direct method. The direct method is, I want this, so I'm going to set up cases for this, and then add them together.
So let's take a look at some more uses of the indirect method.
Mm-hmm. So if we revisit example 6C from last class, okay, that was the one where we were using all the digits from 0 to 9, how many 3-digit numbers have at least 1 5, and we showed you how to set up cases, 1 5, 2 5s, or all 3 5s. So that was a direct method where we said, we want at least 1 5, so we're going to find out how many ways you can get that. We can do it a little bit differently. So if we take all the possible 3-digit numbers that we calculated, that could include repetition, and we subtract the number of ways that you could get a 3-digit number without any 5s, okay? Because if we want to have at least 1 5, then we need 1, 2, or 3 5s. The only choice that's undesirable is no 5s. So if we find the number of 3-digit numbers we can make that don't have any 5s, that's the only undesirable case. So this allows us to use our indirect method. It'll give us the number of 3-digit numbers with 1, 2, or 3 5s. Because you can either have 1, 2, or 3, or none of them when it comes to 5s in there. So if you recall from last time, the number of 3-digit numbers with repetition was 9 times 10 times 10 because we couldn't have 0 first. The number of ways of calculating how many 3-digit numbers without any 5s, you simply just throw out the number 5 from your options.
5 is no longer an option.
Yep, so you go from 10 digits down to 9 digits. So you have 0, 1, 2, 3, 4, 6, 7, 8, 9. So that gives you your 9 choices, but again, the first digit cannot be 0. So you drop from 9 choices to 8 because you have to kick 0 out temporarily. Once you've kicked a 0 out and you go to your next digit, again, it can just be anything but 5. And then the last digit, anything but 5. And because we are doing at least 1 5, we know repetitions allowed, so that's why we're allowed to repeat these values. So if we take the 900 and we subtract the 648, you get the 252, which we calculated took a lot more effort.
Oh, yeah.
Okay? So the direct method will work, as will the indirect method, but when you ask yourself, the number of cases that are desirable here, 1 5, 2 5s, or 3 5s, there's 3 desirable cases, and there's only 1 undesirable case, no 5s. So you will save yourself a lot of energy if you just subtract the 1 undesirable case out.
So really, this is a time-saving method.
Yeah.
But it becomes crucial, especially when we're dealing with bigger problems.
And sometimes, if you try to use the direct method, you would be at it for hours, and the indirect method would only take you 5 minutes. And so you'll see some questions where you really cannot do the direct method reasonably.
Yeah, and you better believe that we're going to give you some examples where you can't use the direct method reasonably.
Yeah.
Okay. So, moving along here, let's talk about some more advanced counting problems. So, we've looked at a couple where we've given like a few restrictions here and there.
Can't be a 0.
Let's
Have to have
really
more than 1
restrict.
5.
Let's really, really restrict.
Yeah.
So, great example. We're going to use the digits 0 to 5. How many 6-digit even numbers over 300,000 can be formed using the digits 0, 1, 2, 3, 4, and 5 with no repetition? Holy cow, we've got one restriction right here.
Even number.
So it has to end in a 0, a 2, or a 4. Of course, we're not using 6, 7, 8, 9 as options, right?
Yeah.
So it has to end in a 0, a 2, or a 4. Over 300,000 means that the first digit has to be a 3, a 4, or a 5.
Yep.
Without repetition, and 0 to 5 means that we're only using 0, 1, 2, 3, 4, and 5.
So we have 6 digits to choose from and no repetition.
And no repetition.
Yeah.
So there's a whole bunch of restrictions in here.
Yeah. And we want to point out, okay, so it has to be 6 digits, so you're going to draw your 6 lines. Has to be an even number, so the last number has to be a 0 or a 2 or a 4. Has to be greater than 300,000, so the first digit has to be a 3 or a 4 or a 5, and 0, 1, 2, 3, 4, 5 without repetition. If you notice that the 2 restrictions at the top, it deals with the first digit and the last digit of your 6-digit number. Notice that there's some overlap. Notice that if it has to end in 0, 2, or 4, but the first digit has to be 3, 4, or 5, then if we weren't planning, if we weren't thinking, then we would have a case where it starts with a 4 and ends with a 4. But we know that repetition's not allowed, so I can't create a case where it starts with a 4 and ends with a 4. So what I have to do now is say, okay, because they have to be mutually exclusive, and right now they're not, then I have to create scenarios where I can separate out these cases so that I can avoid the overlap. Now, you can go either way. You can set up the restrictions on the last digit and then build the first digit in. I find it easier to go from left to right.
Yeah, I find it easier to start with the first digit.
Start with the first digit.
So even though this one's listed first, I like starting with this one. So here are basically our mutually exclusive cases. Bang, bang, and bang. We're talking about 6-digit numbers. So the first digit has to be a 3, a 4, or a 5. So let's lock those puppies into place. Yeah. Okay, so this is a 3, this is a 4, and this is a 5. Now they're in boxes and they're below the spots because this doesn't represent the number of options we have. This represents, okay, this is a locked into place.
Yeah.
Okay. Yeah. So here, this is a 3. Let's talk about the first one on its own first. Yeah. I don't have an option for this.
Yeah.
Right? I don't have an option. But in the last, it's got to be even. So I can choose from a 0, a 2, or a 4. Now, is there any overlap between these?
Nope.
No, there's not. So how many choices do I have in my first spot?
Well, there's only 1 3 to choose from.
So there's only 1 3, so I got 1 choice and it goes there.
Yep.
How many choices do I have for the last spot now?
Well, you've got 0, 2, or 4, so you have 3 choices to choose from there.
Yeah.
Okay.
Once I've used this digit, the 3 is gone, and I've used this digit, either a 0,
whichever
2,
one
or a
you
4,
picked,
whichever one I
pick one
picked.
and put it there. Yeah.
How many do I have left to then fill these?
Well, since we have only 6 digits to choose from, 0, 1, 2, 3, 4, and 5, we've put a 3 there, and then we've put another one of the even ones at the end. So we've used up 2 of our 6 digits. So that means we only have 4 possible values to choose from. And
in the
then
next spot, we'd only have
we
then
can't use
3.
that one again, and then
in
we
this
can't
spot,
use
we'd
that
only
one
have
again.
2.
Yeah.
Okay, so that's the way it's going to go.
Yeah.
And so what we get here is we get 72 different 6-digit numbers.
Yeah.
No repetition.
Yeah.
And these are ones that start with 3. And they're even.
And they're even. And can I note, too, that as soon as you set up your 3 cases, and you make one case where it starts with a 3, one case where it starts with a 4, and one case where it starts with a 5, you can sort of mentally cross out that restriction because you've met it.
Mm-hmm.
So you've set up cases that will meet that restriction. Now you can sort of set that restriction out of your mind. The second restriction you have to comply with is what it ends with.
Mm-hmm.
Okay? And then the third restriction that we build in is the fact that we can only use them once. And that's how we get the 4, 3, 2, 1. We have to keep going down each time because we can't reuse. So once you've built one restriction in by setting up your cases, that one's taken care of. And then you build each case based on the restrictions that are left.
So here's the next one, and this is where some of our logic comes into play. Here I've got 6-digit numbers, but these are ones that are starting with 4. And because these are ones that are starting with 4, how many options do I have for the last digit? It has to be even.
It was going to be 0, 2, and 4.
But I can't use the 4 because I've already used it here.
Yeah.
So I now only have 2 options for the last digit.
Yeah.
So I've got 1 here because I don't have a choice. It's got to be a 4. And I've got 2 here because I've already used that 4 over here.
Yeah.
Again, in the middle 4 digits, I've already used 1. I've already used 1. So now I have 4 options. Now I have 3 options. Now I have 2 options. Now I have 1 option. So what I end up getting is 48 total possible outcomes.
If you start with the number 4.
Yeah. And now if I start with the number 5, again, I can include that 4 again.
Yep.
So I've got 3 options here, and I've got 1 option at the start. I've got the same 4, 3, 2, and 1 options here in the middle. And so really, case starting with 3 and case starting with 5 have the identical answer.
Yeah.
But because these are mutually exclusive cases now, I can have a number that starts with 3 and 4 at the same time. Yeah. Those are mutually exclusive. It either starts with a 3 or it starts with a 4. And there it is, the use of the word or. Yeah. I add these answers together and I get 192. So there's 192 6-digit even numbers over 300,000 that can be formed using the digits 0 to 5 without repetition. All right.
Fancy that. All right. So that example 3, that's a challenging example.
Oh, yeah.
You're going to see one like that on your unit test.
Oh,
absolutely.
Guarantee it.
An n-digit number has to be even or odd. Using these digits without repetition, has to be bigger than this or smaller than this. Like, you're going to see restrictions on the starting value, the ending value, and then how many times you can use the digits.
And you'll see tons of examples in your classwork that we're going to do in class together.
In the textbook too. Yeah. So just maybe put a star next to example 3, and if you don't fully understand it, then that is a question that you want to get managed when you get to see us in class. Okay, so let's look at example 4. Brittany's writing a multiple choice quiz. It consists of 6 different test questions, and each question has 4 possible answers. How many ways can she complete the quiz, assuming that she does answer each question? Okay, so, well, she's got 6 questions, so there are 6 stages where she gets to stop and make a choice. Okay?
So
we'll
this
draw
really
the 6 lines.
Is very, very similar.
Yeah. Now, at each stage, she's got 4 possible choices. Say she's got A, B, C, or D. Now, we've removed the option for her to leave it blank, which would introduce a 5th option. Okay, but for right now, she's going to fill in a bubble. She's going to guess, even if she's not sure. Yeah. So that means she's got 4 choices for the first question, 4 choices for the second question, and so on, all the way through. So that really it's just 6 stages, 4 choices at each stage, 4 times 4 times 4 times 4 times 4 times 4, 4 to the exponent 6. So she's got 4,096 possible ways she could complete the test if she answers each question. Okay, so let's look at the next example. Let's say we've got a score at halftime for a football game is 5-2, And we want to know
soccer, European football.
European football.
Yeah.
Okay. How many different scores were possible after the first quarter? All right, so we've got two teams. Each one has its own score. We can make choices at two different stages. So we're going to sort of say, all right, we got a team 1 stage that we got to make a choice for, and we've got a team 2 stage, so we can draw our 2 lines. For team 1, at halftime, their score is 5, which means that before that, it could have been anything from 0 to 5. Okay, so they could have been 0, 1, 2, 3, 4, or 5.
Mm-hmm.
Couldn't be 6, 7, 8, 9, or 10, or anything else, because if we're going back in time, then it can only be less than what it was at halftime, if we're going back to the first quarter. Team 2, which had a score of 2 at halftime, can either be 2, 1, or 0.
Yeah, because 3 is not an option. They haven't scored 3 goals.
They haven't scored 3 goals yet. So again, we're going back in time. We're saying, what are some of the other possible scores that there could have been if the score now is 5-2? Okay, so there's 6 choices for Team 1, and there's 3 choices for Team 2. And again, we're choosing to put a number into each spot, so 6 times 3 is 18, which means that the total number of first quarter scores, reasonable first quarter scores, would be 18. Yeah.
All right. So here we go. Student council forming a committee with 3 distinct positions: president, vice president, and treasurer. Student council basically has members in grade 9, 10, 11, and 12. There happens to be 4 grade 12s, 5 grade 11s, 3 grade 10s, and 2 grade 9s on student council. So first of all, let's diagram that. So we've got 4 in grade 12, 5 in grade 11, and so on and so forth. We have 14 total students.
Yeah.
9 of them are seniors, 5 of them are juniors.
Sounds good.
Okay?
Yeah.
So how many different committees are possible? Again, we're starting out by saying how many different committees are possible.
We need a president, we need a vice president, and we need a treasurer.
Yeah.
There are 3 roles we have to fill.
Yeah, there's 3 roles, 3 stages, 3 spots, and here they are. We've got 14 options. There's 14 students that could fill this first role. There's 13 positions that could fill this second role, and there are 12 positions that could fill this third role. Why haven't we allowed for repetition of digits?
Well, because we don't want repetition of people. We don't want the same person inhabiting 3 different roles. Then that means as soon as we've used up a person for president, then they're no longer in the race for vice president. And then once we've got that person, they're no longer in the race for treasurer.
So the total number of different committees of president, vice president, and treasurer that are possible is 2,184. So lots of different ways we could fill those roles.
Yeah.
How many committees, though, are possible in which there are 2 senior students and 1 junior student? So let's say that we said, okay, out of the president, the vice president, and the treasurer, we kind of want representation from the seniors and from the juniors. But we want 2 senior students and then 1 junior student. So out of these 3, now we have to think about this. We can say, oh, well, we can put this junior into several different roles.
Yeah.
So here we basically go and we can say, okay, here's one scenario. We've got the president is a senior, the vice president is a senior, and the treasurer is a junior.
Yeah. This reminds me of the ice cream cones.
Yes,
senior,
exactly.
Senior, junior.
And so this is another archetype of problem, right? It's a type of problem that we're going to see over and over again. So here's another scenario. The president is a senior, the vice president is a junior, and the treasurer is a senior.
Senior, junior, senior.
And of course, the last scenario...
And you're following along with us, just like the ice cream.
...is that you have the junior is the president, the vice president is a senior, and the treasurer is the senior. So how many different committees are possible in which 2 senior students and 1 junior student? Well, now we go through and we have to be specific, because in this case right here, how many seniors do we have to choose from?
Well, if we're making our first choice, then we still have 9 seniors to pick from.
Yes. How many choices would we have here for the vice president once this person's been filled?
Then we're down to 8.
Yes. And then for the treasurer, it has to be a junior, so we only have 5 choices. These are mutually exclusive cases because you can't have a president who's a junior and a president who's a senior
at the same
time.
Yeah.
It doesn't work. Those are 2 different people, And so these are mutually exclusive. So what do we always do with mutually exclusive cases? We add them together. So here we go. We got 9 times 8, because we can't repeat, times 5, because there's 5 juniors. Here, again, we're going to start with our restriction first. There's 9 options for the senior president. There's 8 options for the senior treasurer. And then there will be up to 5 for the junior vice president. Again, the same thing here. And so when we multiply these out and then add them, what we get is 1,080 different committees. So again, our restriction have cut down our unrestricted number of committees. Okay.
Now, I'm going to just make a statement that you could go back and do that question again using the indirect method. Because if we had 2 seniors and 1 junior, then there is a way to go through. Like, there are always, just to keep in mind, there's always multiple ways of doing this. Because we're familiar with this, and because we can set these up rather quickly, then we chose a direct method here. Okay.
That could be done using the indirect method.
You could, You'd have to do a little extra thinking, but yeah, you could definitely do that with the indirect method. 8 dogs are competing in the Doggy Olympics. This is a special event that comes around every 8 years, okay? So, in how many different orders could those 8 dogs finish this important race? Okay, well, since there are 8 dogs...
There's only 8 dogs selected from all across the world.
All across the world for this. So you've got 8 dogs. Assuming they all cross the finish line, then there are 8 different positions that they can finish in, right? So again, we draw our 8 lines. They could finish 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, or 8th. For first place, no dogs have crossed the finish line yet, so we have 8 dogs to choose from. Once that first place dog crosses, there's still 7 that have not crossed yet. So we're going to do our 8, 7 times 6 times 5 times 4 times 3 times 2 times 1, which gives us 40,320 total finishes.
There's that
with
many
all 8 dogs.
Basically, we could have that many different orders of a finish for a race.
That's why it's not great to bet on dog races. Too many choices.
Too many choices.
Yeah, too many choices. Okay, now this was finishing the race, which means all dogs all finish 8 spots, right? How many ways could we do gold, silver, and bronze collars?
Yes. Okay. So we don't give dogs medals. We give them collars. Gold, silver, and bronze collars.
And so how many ways could these 3 positions, first place, second place, third place, be awarded? Well, again, so now instead of finishes, instead of all 8 dogs, now we only care about who runs across first, second, and third. So we have 3 spots to fill. Again, in the first place position, we've got 8 dogs to choose from. Once we've used up that dog can't win gold and silver. Okay, so then we've got a different dog to choose from for silver, and then a different dog to choose from for bronze. So we got 8 times 7 times 6. So the total number of ways that these gold, silver, and bronze medal collars can be awarded is 336. Okay. All right, so let's say of all these dogs chosen,
8 dogs in the world,
all across the world, Chuck, your Chihuahua, is one of the doggies chosen. How many possible finishes, Mr. Jackson, how many possible finishes would include Chuck winning a collar?
Well, to do this, what we need to do is we need to be very selective, because winning a collar implies that, okay, well, he could actually win the gold collar or the silver collar or the bronze collar. So again, we're being almost, silly in how much we're pronouncing or, because what this is implying is we're looking at mutually exclusive cases. So here's 8 dogs finishing the race, right? Total possible finishes. Here's Chuck. This is where Chuck comes in first. Here, of course, what we'd have is that if Chuck comes in first and we want to ensure that he comes in first, he's not even a choice anymore.
He's just one dog.
He has finished first. That means that there's 7 different dogs that could come second, 6 that could come third, and so on and so forth. So there's 5,040 different ways that race could be finished if Chuck comes in first place. Now, if he finishes in second place, it's the same order of numbers, right? It's just, if he finishes in second, now we don't have an option for him in second. There's 7 dogs that could finish in first, 6 that could finish in third, and so on and so forth.
Yep.
Still 5,040. And yeah, you guessed it. If you're doing this and you're thinking him finishing in third yields the same result.
Same exact result. Yep.
Okay. So again, mutually exclusive cases. We're going to add them up, and we're going to say, okay, there's 15,120 ways. Basically, the number of finishes with Chuck in the medals is 15,120. Now, this is final thought here on this question is to say, how many possible finishes then would leave him out of the standings, out of the medals? So let's say he doesn't win the gold, silver, or the bronze. Well, this would mean that he could win 4th place, or 5th place, or 6th place, or 7th place, or 8th place.
You're welcome to use the direct method.
Yeah, I could use the direct method. I could calculate all of these cases and add them up. But that's a lot of work. So what I would prefer to do is to use an indirect method to solve this problem. The total number of finishes that we established in part A.
Without any restrictions
without
on
any
Chuck
restrictions
or anybody.
at all. And I subtract the number of finishes where he does win a medal.
Some kind of a medal.
Right? Is going to give me the number of ways that the race can be run without him winning a medal. And so because I've already done these things, I can simply say, 40,320 minus the 15,120 ways that he does win a medal gives me 25,200 different ways of not winning a medal. And so that is the perfect use of an indirect method, where we've done all of these things together, and now I don't have to calculate case, and then add them all up.
Exactly.